So I'm pleased to introduce Michael Kosorok. He is the W.R. Kenan Jr. Distinguished Professor of Biostatistics and Professor of Statistics and Operations Research at University of North Carolina, Chapel Hill. He got his PhD at University of Washington in 1991. He is an expert in precision medicine, data science, and machine learning. He's going to talk to us today about recent developments and future possibilities in precision health. Dr. Kosorok, take it away if you are ready.
Thank you. I'm very happy to be here. I'm going to share screen and get my talk on here. And can everybody see it? Yeah, great. All right, well, thank you again for the invitation. I'm really happy to be here. University of Michigan has done a lot of very important pioneering work in precision medicine and precision health, and still are. And it was a delight to meet with people so far. And this plot here I have is a plot of, I'll talk a little bit more later. It's some data from a patient with type 1 diabetes in one day in their life, and I'll come back to it and discuss it a little bit later from a project we're involved in. Today I'm going to just talk kind of at a high level about the concepts of precision medicine, precision health. Many of you know this area well and have contributed to the literature. Some of your faculty have done so, and some students are working on this as well. And I'm going to talk a little bit more about the sort of decision support aspect of precision medicine, precision health. And what I'm referring to is data-driven decision support for treating patients in the presence of heterogeneity. Treatment examples might be considered could be drug choice, dosage, timing, administrative actions, a variety of other ways that treatment might be modified. And we want to develop algorithms and methods that allow us to do this and adapt to a patient in a way that's reproducible and generalizable. It's empirically and inferentially valid. So we want to have statistical validity of our approaches. Precision public health, from my view, is similar decision support, but here we might have communities or families, clinics, social networks, other entities besides an individual being treated. And sometimes policies for how to control an infectious disease that a county might adopt could be one of those types of things we could consider. And precision health is really the union of all of this. Precision medicine, precision public health, they're integrated in various ways, but the idea is to try to use data-driven ways to come up with decisions that need to be made in these settings. And our approach is to try to look at the entire population of patients and see how we can look at that and determine which patients should get which kind of treatment or which clinics should get which kind of policy and so on. But we're not looking at another approach to precision health and medicine is to develop a drug based on a particular specific biomedical pathway, and then identify patients from whom that drug would benefit them. And this is one way that this is done, but from a public health perspective, that can be viewed as drawing energy and effort away from the population as a whole. It may not benefit everyone. And so we're looking more at the population-based approach. While it involves tailoring treatment or to individuals in that, is done in a way that the population benefits. But that's the goal anyway. So dynamic treatment regime is a very key part of this. And this is either a single rule or a sequence of rules that are based on patient level characteristics, either the patient as they present to a clinic, or maybe as collected over time in a series of treatments and clinic visits. It's dynamic in two ways. One is it depends on the individual's characteristics. Two is sometimes it can also adapt over time. But it's dynamic in both of these ways. And it clearly fits into the precision health paradigm because individual heterogeneity is used to inform the treatment choice and help us know how to optimize the result, the treatment choice for each person in the population. So just to give a little bit of some specifics here, that usually in these situations, let's consider first a single decision that's going to be made. We would have tailoring variables. These are variables from the patient that reflect something about them that we think is important in determining treatment. It could be biomarkers, it could be demographic information. Then we have a choice of treatment and our potentially modifiable risk factors, things that we think if they've changed or if we do them in a better way will improve the patient's outcome. But they're the candidate treatment choices. And then we have a vector or scalar in some cases of the outcome of the patients. This would be, for example, one might look at total survival time, maximize that. Or it could be, a vector could include various side effects, quality of life, and survival time. But these three variables are important ingredients to this type of precision health we're describing. And if it's a single decision setting, we would typically have this type of data available. And it could come from a clinical trial where maybe the treatments in A were compared, but after the trial's over, we want to figure out which subgroups would benefit from which treatments. Sometimes this can significantly important subgroups can be found even if the treatment is on average not effective equally for everyone, or the new treatment, for example. Other times it can further enhance the performance of this by realizing that not everybody benefits. Even though it's on average beneficial, there might be some subgroups who do a little better if we just stick with the standard of care for them. In a multi-decision setting, one would have a sequence of this kind of data, a series of this kind of data over time, and one would want to make good decisions for treatment at each of those times based on the historical data available. Infinite horizon is a slightly different case. Multi-decision might be where cancer chemotherapy is involved, where there's 1 or 2 or 3 stages of treatment. An infinite horizon is where there's multiple recurrent cases of treatment and decisions that need to be made. And this is often associated with chronic health problems. It could be psychiatric challenges, behavioral challenges. Also a project that we're working on, and actually some people at the University of Michigan are, on back pain. It's called the backpack study, where that's a chronic condition, and that could be definitely a benefit from, for example, potentially an infinite horizon approach where one expects this to be an ongoing situation with multiple decision times. And the goal is to try to benefit and maximize the clinical and quality of life outcome for a patient. Okay, and important thing to mention is that this is all firmly within the causal inference framework. Causal inference is sort of the basic premise or under the theory that underlies these approaches. I have a little example of an unusual DAG, perhaps, for a 2 decision time situation. There's X1 is at time 1, we have patient presenting at baseline, and then we want to know how to treat them. That's A1, and then that affects the next, the state of the patient at the next time. And now we have additional information at X2, which could be combined with X1 and the knowledge of the treatment used. And that could be used to decide which treatment A2 we give them, and all of that can affect a final outcome. So dynamic treatment regimes choose essentially among causal models to obtain treatment algorithms which optimize a specified utility as a function of individual level characteristics. An important component of this for observational data is, and actually for experimental data as well, but for observational data, we need to look at the propensity score. This is an estimate of the probability of getting different treatments for each of the different types of patients in the study here. And for observational data, if we want to compare treatments in all the subgroups that we're interested in, we have to have a positive probability of observing that so we can make those comparisons. And in these and in randomized studies, especially for example with SMART, we would know the propensity score, we wouldn't have to estimate it. And also many of the assumptions that we would need in observational data can be satisfied for a well-designed SMART study, for example, although some of them we have to be careful with. But in any case, potential outcome validity is important. No unmeasured confounders, or in the case of a sequence of treatment decisions, sequential ignorability is important. And then positivity over X for each of the treatments we're interested in is important if we want to make comparisons with those in those subgroups in our methods for doing this. Now, I said it's sort of a high-level talk, so let me try to now fold in a little conversation about machine learning and AI. Prediction is a common goal of machine learning and AI, but it does not necessarily provide meaningful decision support. Specifically, while it's useful, we'd like to look and explore, and we've been working on this, and others have, including people at your department, how you could extend prediction to more precise decision support things. And these are more difficult to do than prediction. So the first step past prediction is be able to come up with models that are causally valid in the sense that we can do what-if analysis. What if we change this? What if we change this treatment or this treatment? How will this patient respond? And that's more difficult than standard prediction, more granular. And then decision support is not only goes another step and says, what is the actual optimal sequence of treatments that I should be giving to each of this patient as I go forward in treating them? And that may be based on the current available information or the history of information. And so that coming up with that optimal treatment can be a non-trivial task, but that's really one of the ultimate goals of precision medicine, is this kind of granular decision support. Now, methods for machine learning are useful in this setting, and especially for dynamic treatment regimes. But I just want to say generally that when we think of machine learning and AI, a lot of you in the department use this, but there historically has been a separation of statistics and machine learning and AI, which is completely unnecessary. There are different traditions intellectually that led to different discoveries in these fields, but really it's about data and about prediction, about estimation, so it is part of statistics. But when we think of machine learning statistics, we think of classification and regression. But a lot of, from other disciplines, a lot of other tools have come forward that are very, very, very useful to solving sort of various kinds of problems from data. And one of those is estimated dynamic treatment regime. And reinforcement learning is a very, very powerful tool. In medicine, when we're looking at dynamic treatment regimes over time, we have to use an off-policy version of reinforcement learning, usually because we can't give more than one treatment at a time to a patient, and we can't repeat the whole process with that patient once they've gone through the disease with another treatment. And on-policy means that we're able to freely experiment and try different treatments to a certain extent, but we have a limited amount of such that we can do with patients. And this leads to interesting results that if we're careful in our analyses and our design and the processes we use, we can actually estimate an optimal policy or treatment sequence, even if nobody in the study actually receives that optimal treatment. It has to do with various methods of comparing similar patients at different times, combining patients that are different at one time but similar at other times. But we can do this validly in statistics. Deep learning is another tool that is becoming more and more part of biostatistics. And here, this can be very useful, but one has to be very careful. We're beginning to observe that deep learning is very, very good for certain kinds of problems and actually not so good for other kinds of problems. Sometimes a lasso with an elastic net penalty may be better for certain kinds of problems, maybe sparse regression in high dimensions. But if there's a little bit of interactions and other things going on, a random forest is maybe better. If it's an abundant high dimensional regression, like using images for prediction, then deep learning begins to be very, very useful, even with moderate sample sizes, in some cases, of even like between 100 and 200 observations. But these can all be brought into this precision medicine endeavor. So one of the other things I like to mention is a distinction between predictive and prescriptive decision support. And prescriptive is something that is a little more useful to many clinicians, and I'll try to distinguish those. But let's just consider a situation where we have features of the patient covariates X. We have treatment A, and let's just make it binary. 0 is standard of care, and 1 is this treatment that we're looking at. Then the outcome of interest, let's say overall survival time. I'm ignoring censoring at this point. Then Y can be shown to be equal to a prognostic effect plus a treatment interaction effect plus residual error. And this is a totality. These are really just series of conditional expectations you can set up. And this is really what would happen, what happens to be with relatively weak conditions for an outcome Y. The point I want to draw your attention to, is the prognostic piece is f of x. And that will not give you any information on how to treat this patient. It's only g of x that will give you that information. In this particular case, the optimal treatment is going to be based on the sign of g of x. If it's positive, you take treatment 1. If it's negative, you treat treatment 0. And so the sign of gx would give us the indicator of what to do in this case. The point is, prescriptive, which is g of x, versus prognostic, f of x, are very, very different. And a lot of the work in precision health is focused on clustering and other things to look at subgroups without treatment factored in, thinking that, okay, we'll take these and now we'll go to the next step and use them for prescriptive purposes. But in the biological sense, there's no reason that, that prognostic variables would be of any use to us necessarily in the prescriptive side of things. They're very, very different. And it's important to keep that in mind. Now, sometimes they will overlap, but it's important to not assume that they're related, and that one can learn about treatment allocation from the prognostic piece of this. So the decision support is more focused on the estimation of G here. Okay, so a couple more thoughts on excuse me, a couple more thoughts on the single decision setting. Here, regression can be one tool that's used, a regression model that fits those terms, and then you basically maximizing, which in this case would come, that I just mentioned, would be looking at the sign of G. But there might be more complications. There might be more treatments. Treatment could be a continuum instead of a finite set of treatments, but you could still use regression maximization to get at an optimal algorithm from that regression model. And frequentist and Bayesian tools are both good in this. There are some settings where it's a little easier to use frequentist and others where it's a little easier to use Bayesian methods. I find that I go back and forth between the two and sometimes use both in the same context on occasion. And machine learning and the things that we learn from machine learning are very, very useful here. The artificial intelligence tools can be very beneficial. When we get to the multi-decision setting, we really need off-policy reinforcement learning for most of our medical questions. There actually are some examples where on-policy can be helpful, but generally for a lot of the standard medical situations, off-policy is the most useful. Q-learning is especially useful because it's nice to introduce it as a reinforcement learning because it breaks down to a series of regression models in which we could do exploratory data analysis, explore their validity and check at each step in the process. And there is software for doing this that's available. Outcome-weighted learning and policy search-related methods. The focus here is on actually looking at that G or the sign of G, find that policy, and are there ways that we can do this without having to do regression modeling also? And the answer is yes. And one of our early papers on this, which is the outcome-weighted learning idea, we learned that you could convert this to a classification problem in the single decision case, and it turns out in the multi-decision case as well, but in the single decision case, consider a randomized trial where we collect a lot of feature variables and biomarkers, knowing they may be useful for analyses later. And we randomize 50-50 to placebo and active treatment, or standard of care and an active treatment. And then we have an outcome Y that we want to maximize. Well, what we found you could do is if you take that X and use it to classify A, the treatment received. Now you might say, wait a minute, that doesn't make any sense because A is independent of X, right, by design. And that's absolutely true. So that would be a terrible idea. However, if you take each of the individual errors in your classifier and weight them proportional to Y, the outcome, or bigger Y is better for the patient, and then you do that weighted classification, that is actually exactly getting at which treatment they should have received, even if they didn't get that in the actual trial. And so that gives us the opportunity to bring in a lot of machine learning tools and various nice properties of machine learning into the process. And there are various other approaches. There are certain types of regression robustness you get, and if you do double robust versions of this, you actually get a lot of stability, and you can bring in extra information from the regression model if it's close to right. And it performs quite well, and it's been worked on by many individuals, a number of whom have been in this department at University of Michigan. Okay, so that's just a high-level conversation about this connection between the task of decision support and machine learning. And now I want to completely change gears for a minute and talk about artificial intelligence. So what is intelligence? Well, this has been a question of debate for a long time. Is it to think or act like people? The earlier quest in artificial intelligence focused on trying to mimic a human thought processes. And a Turing test was the idea of if I couldn't tell the person I was communicating with was a machine or a person, I couldn't tell, then that means I was successful with the AI. But it began to be clear that really we're more concerned with having AI be useful for us rather than just replace us. Also, that's very hard to fully replace us. And there are things that we want it to help us doing. For example, it can work with huge amounts of data quickly. It can perform some tasks people can perform maybe more efficiently. It can reason logically. It can help us in making decisions, as we've talked about decision support. Now, it can also learn how to act optimally if we tell it the optimality criterion. It solves a problem like we just discussed. But what about reasoning morally? Can we train that to happen? Depends on various nuances of that, but that gets to be very difficult. And I had a conversation with one of my friends who is an associate dean in a school of arts and sciences, who's an anthropologist. We had gone to New York for some sort of thing, helping with the UNC, and I can't remember what it was right now. We had talked about, what about art and artificial intelligence and art? There's been various efforts at using AI to develop poetry, to write music, to mimic Mozart, for example, and to draw and do other arts. And my colleague is an artist and I'm a composer, so we were talking about this, and we really just felt that it was very unlikely that in the immediate future this could be something that could be done. The music software and other things can mimic and create new things, but especially in the music world, it's difficult to create something that's surprisingly new, surprisingly elegant. The things with the Mozart imitations sound a little bit like music for a while, but it gets kind of boring. It doesn't have the intriguing long-term dependence that Mozart and Beethoven and other composers had. And it sounds a lot like music that's already been written, or at least samples from music that's already been written. And music and art should also bring new things to us. And he was talking about how when he draws things, he looks for something kind of surprising and unusual to draw. And he doesn't know you'd have to train AI to do that, but would it be able to have the same sense of wonder that a human has when they make an artistic decision? And so maybe down the road, but right now it's not quite there. What do we want computers to do? We want them to be able to make rational decisions, achieve predefined goals. That can be very helpful. That's used in robotics and other areas. And we can have them help us optimize predefined utility. But can a computer decide what utility or set of utilities to use? That's a little bit trickier. So I already mentioned the 3 stages of prediction, but the point is that causal validity models and also decision support are things that AI can help us with. But I just raise these issues that there's other interesting things that could be done, but AI has a lot to go before that, and a lot of people now are focusing on pragmatic AI, or things that will actually help us. And I want to mention something that I think is interesting about AI. It's been studied quite a bit, and there's these winters that happen. Usually what happens is a really cool idea emerges, and it begins to be really exciting. People get interested in it, and then it begins to oversell itself and say we can solve all these problems. And then things don't work as well as they thought they should, and then people start becoming disenfranchised. And this happens repeatedly. And some people say that we're sort of possibly heading towards another winter. Right now, it's not clear. But one of the things that has been happening all along and during these winters is several scientists have continued to work on problems that are no longer there's not a lot of hype about them, but there is potential. And some of these older ideas have been refined and improved upon. to lead to some very, very useful AI today. And I just want to mention this because it's important to be aware of the cycles in research, whether it's AI or any field, where there's hype for something, a lot of excitement. I like to warn students and other young faculty to don't always go after what looks like the most exciting thing. I think it's okay to do that sometimes, but try to be a little bit judicious that sometimes hype is just that, it's hype. Other times there's a kernel of truth, and sometimes it takes a little bit of time to figure out what's happening, but we need to be aware of this possibility here. I also want to talk a little bit about the dark side of artificial intelligence. And you may be asking, why is he talking about artificial intelligence? This is the biostatistics department. Well, I want to say that anything involving data and analyzing data is part of especially if it involves health, that should be part of biostatistics. We don't have time to do everything in every field, but certainly this area concerns us. And there turns out there are a number of biostatisticians and other statisticians contributing a lot to the AI, ML developments going on. And our group has been very interested in this, and I know that some of you at University of Michigan Biostat have been doing some of these things as well. So I want to talk a little bit about some of these things and to worry about them, things that you can worry about a little bit, but I hope there's solutions too. The democratization of AI, really right now it's very easy to download software that can do deep neural nets. And the pros is the good thing about this is it can lead to greater awareness of AI and citizen science progress. The cons is that this is giving a lot of people basically a loaded weapon. If they have insufficient understanding of statistics and other important principles like reproducibility, there'll be too much false positivity, too much unhealthy hype, too many wrong and unfortunately highly influential results obtained. And I know that we've experienced some of these, you're aware of some of these things. And so this is something that one has to be very careful about. Another concern is the risk of bad actors. Evil people could use AI and decision support to harm individuals. And also automated AI tools could have unintended adverse consequences. For example, some decision rules could have unintended disparities that might affect particular subgroups unfairly. Or as is the recent issue, although I think it's been addressed to some degree, Facebook's machine learning tool for trying to maximize clicks has been shown to actually provoke discord and conspiracy theories in the society itself, because so many people are users of this. And I believe that there's been some significant work by the CEOs of these companies and others to try to change that. But these are possibilities when one uses these very, very powerful tools and are not careful. Good research takes care. Well, sometimes we do need to work quickly. It shouldn't be the thing we do all the time. Easy implementation leads to impatience in the research process and even maybe an unwillingness to learn enough statistics to be able to be sensible about research. This could lead to also inadequate evaluation and peer review. One of my clinical collaborators showed me, presented to our lab a review paper recently in one of the disease areas, and that COVID-19 has induced a huge amount of flurry in science, and it appears to be a lot of increased number of papers accepted and a shortening of the review process, and many people feel severely endangering the quality of the review, and a number of unfortunately not great research has come to be quite prominent before it's been withdrawn. And so one has to be careful with going too quickly. Obviously we can't take forever, but we need to be careful. And promising, and this can work on getting, this could work in two ways. One is if we're not careful, something that is not so great becomes used quite a bit before it's found out that it's doing bad things. On the other hand, also promising advances could be dismissed prematurely. So it can go in both directions. Study design is really crucial as a part of AI and machine learning. People focus a lot on the observational data, which is good, and data that's available, which is also good. But so much improvement could happen if we designed a lot of these data sets, even routinely collected data sets, if design was factored into it, we could improve the quality of our machine learning predictions by many folds, thousands or more. Okay, you'll notice I have a picture here of this piece of paper with lines, straight lines and squiggly writing. This is a photo of of original score from Beethoven's Fifth with his own handwriting. And the Beethoven's Fifth Symphony, a lot of you recognize it, it's a pretty famous symphony. However, from a composition point of view, it's quite unique. It's really viewed as one of the great events in the history of art. The level of brilliant innovations that he put in this symphony, the idea of using a tiny motif to generate an entire symphony and doing it so masterfully. This really changed the entire world of music. But he did not write this as quickly as he did his other pieces. It took him several years to write this symphony. And this is a full-time composer who was incredibly fast when he needed to be, or could be quick. He was just brilliant. He took time because he wanted to really have an input. Now, obviously, this is not exactly the same as AI machine learning, but I want to remind everybody there is value in taking time to do high quality work. And I have to confess that I'm one of those people that has done quick research, because sometimes we have lines we have to work with. We have other deadlines, although I've never tried to sidestep the peer review process or other things, but I feel there are times when I've rushed things when it would have maybe been better had I been taken time. And we have to find a balance. We can't take forever with these things. But I think it's important to recognize the value of doing things right. Okay, so that's a high-level discussion. I think it's important just to note that we're at a very interesting crossroads in data science and in biostatistics, where a lot of different disciplines are coming together to work. And we have a rich opportunity with all these tools to think about how to bring them effectively into the biostatistical problems. And so I want to talk about, I presented the graph earlier, just a couple examples really at a high level. This is related to trying to help patients with type 1 diabetes. This relates to mobile health and various methods of automated surveillance. This is data from a patient where we're able to collect from this patient in real time their insulin boluses when they received insulin, their glucose level, and reminder that too high is not good, too low is not good. Somewhere between 70 and 120-ish is really ideal. This patient went too low later on and was too high for a long time as well. It's very challenging to keep the glucose level at the right place because their pancreases don't work as well as people without type 1 diabetes. The blue circles here represent activity, with the center of the circle being when it initiated and the size of the circle being the length and rigor of the activity. Similarly with food, center of the circle is when the food was eaten, and the size of the circle is the amount of food. And if we look at this with that information, we can see that this patient has relatively high glucose levels, and they start exercising, and that takes glucose out of the blood quite quickly. Unfortunately, it's dangerously quickly. They go a little too low for a while. They take some food to bring it back up. It goes a little bit too far up. Then they have an insulin bolus that goes back down, and they're kind of starting to keep it close to being within range. But you can see it's challenging. And this is a patient that was, doing the best they can to follow the requirements they needed to stay healthy, but not a lot is known. There is this idea of a pancreas that's had some success, but generally speaking, exercise is a healthy thing to do, but it also endangers and worries patients with type 1 diabetes, and if they're not careful and strategize carefully, they might suffer from glucose imbalance. I want to just mention that hypo or low glucose is actually much more dangerous, but they're both dangerous. Okay, so our goal was to find a way to learn how to guide a patient to optimize the time within safe range in this situation in the context of having them do exercise. So how could we help them themselves strategize for exercise so they can have a safe experience and then continue to stay in the safe range throughout the day? Okay, so that's the framework. And what we use is a Markov decision process framework. And the idea here is you have a sequence of time points. In this case, the time points are quite frequent. They could be 15 seconds, which is about right for this particular thing. The data comes in actually at different levels of granularity, but averaging them within segments can lead to a reasonably good Markov process. And we have the time points, and S represents the state of the patient. And in this case, this is oftentimes when we think of Markov processes, we think of a finite set of states. In this case, these are Euclidean, vectors of Euclidean variables like we would collect in typical statistical analyses frameworks or for clinical data. And so the states here live in Euclidean space, and actually Markov processes are comfortably generalizable all the way up to the generality of the metric space. In this case, we just need to have the Euclidean space, potentially high dimensional Euclidean space. So S is the state of the patient. It may include some baseline data. It can include data that summarizes recent history and going a little bit past. Sometimes we find it's helpful in type 1 diabetes to go back 2 hours and summarize the data that far back. So these can be hundreds of dimensions. And then we have actions that are taken, different things that patients can do. And then we have their follow-up state, and a utility is a summary of this. So the state includes glucose measures. So in this case, we're using the utility, we're summarizing it by the proportion of time within safe range. We want to maximize that for this patient. So what we developed is something called V-learning. Came out in this year's Journal of American, one of the issues this year, so in Journal of American Statistical Association. This is the basic framework. We applied this to some mobile health data, and this is observational data. So what the patient does is not prescribed in this data. It's not a study, randomized study, but the propensity score showed that there was sufficient positivity that we were able to explore these various treatments. And we applied this to some data, and the state include insulin use, food intake, history of these, physical activity, blood glucose. Possible actions included taking another insulin bolus, eat a snack of a certain size, exercise, and combinations of these. So the action space was somewhat large, about 10 actions, I believe, if I remember right. The outcome, as I mentioned, was, in this case, you could do it either out of range and you want to minimize that, or in range and maximize it. Simulations verified that this actually worked quite well. And in this data set, we estimated that we're able to find an algorithm, a better dynamic treatment regime for the patient that was able to reduce their time out of range by 64%, which is significant. So, and that's still work in progress. We're actually working on making this a prototype that we can work with patients. It takes a little while once you have an idea like this to get it actually working with patients, and we're still in the process. We have had several focus groups work with us so far, though. Okay, second example is completely different. So that example uses infinite horizon off-policy reinforcement learning. The next example uses something called inverse reinforcement learning, which I haven't even mentioned. So before I explain the context, the disease context, inverse reinforcement learning is very different than reinforcement learning. What you do is you have a sequence of data, and you have expert decision makers. And what you want to do is you want to infer from their actions taken in the outcome, and the vector of outcomes is, what is the utility? What is the combination of those outcomes that the person is trying to maximize? And this can be done even if the person's not conscious of it. And this is inverse reinforcement learning. However, it typically assumes that the person knows exactly what they're doing and you're just trying to figure it out. However, in the case of treating patients, we know that clinicians are definitely doing the best, and they're doing incredibly good work, but they're not always fully conscious of what they do, and they make there's a possibility that they make error. And so we want to factor that into the reinforcement learning. And this is also allows, and so let me give you the context before I get ahead of myself here. This is studying bipolar disorder. This is this particular study we're looking at called the Systematic Treatment Enhancement Program for Bipolar Disorder Standard Care Pathway. STEP-BDE SCP, one of the longest acronyms I've ever dealt with. And this is published data, and we've got permission to use it. And there's several components to this. There's a randomized trial, and there's also an observational study. What we're trying to learn is how to treat patients who have bipolar disorder. And there's several challenges, and right now we're focusing on how does a clinician weight two different outcomes. In this case, depression and mania are the two things that can happen, but they're kind of opposites of each other. And antidepressants to treat depression can help the depression, but sometimes if it's done at the wrong time, it can induce mania. And so one has to be careful in deciding when and how to treat depression. And so our particular goal here is to find out how do clinicians decide the relative importance of these two outcomes in the utility function that they're optimizing when they make a decision. And we're assuming that we allow that there's a possibility that they will make an error, but as long as they get it right with a non-zero probability, we can infer what their weighting is and how it might change from patient to patient based on that patient's clinical characteristics. Here's a situation that observational data is very, very differently used. Typically, the way that the propensity score is something that's sort of a nuisance, and we try to deal with it so we can kind of make it look like a randomized trial. Here we actually want to learn about the decision-making process. And so it's kind of an interesting use of observational data and the causal framework. So we developed this method, and it led to an estimator that where the parameters in the estimator were square root of n consistent, but it was not asymptotically normal. It ends up being kind of an unusual functional of a Gaussian process. We have to use the argmax theorem to get everything to work out, and a few other function analytic tools to get the bootstrap specialized smooth bootstrap to work. But when we applied this data to the study, we were able to find that there was indeed something that clinicians were doing that led to improvement, and if we could do it without error and help them, we could find the rule they were using so they could apply it without error. Now this is all approximations, but nevertheless, it was pretty intriguing, and simulations show that this works as well. But in this situation, we're able to find a 7% improvement of outcome by doing this, figuring out what they're doing, and then reducing the error in the process, and it's statistically significant. If alternatively, we balance, well, okay, let me first stop. One of the interesting things we found is a key tailoring variable that emerged is the history of substance abuse tend to affect this decision, factor into this situation quite a bit. Also, if we looked instead at balancing between depression and side effect burden, we get a larger improvement at 9% that's also statistically significant. Now, you might say, well, what about 3 or more utilities? Yes, that's something that's important, but the nice thing about using 2 utilities and balancing them is you can prove that any logically consistent combination utility function from balancing 2 competing utilities has to be a convex combination of the 2. But with 3 or more, it's not so clear what are optimal utility functions, although one can still use convex combination, but that's work in progress. Okay, so there's a couple of examples of some, I think, fun projects that draw upon the various tools we've talked about. Excuse me for a minute. What could the future look like? Well, this is a very complicated schematic, and I could have made a linearization of this, but I just want to talk about the high-level ideas of what things look like in the future. Well, the idea and the big picture of this is, couldn't we have real-time automated data collection, which real-time evaluations that well-designed, that allows us to continually develop optimized algorithms for treating patients, for individual patients as well as for clinicians making decisions, that is continually updated as we get new data. Well, that sounds nice theoretically, but there's some issues with it. One theoretical or philosophical issue is if we optimize on all the data we have and give everybody the best treatment right now and forever, or immediately start doing that, that sounds good, but that's a greedy approach, and what it does is it ossifies the algorithm. And the challenge with that is if people age or there are other changes in the environment we live in or new drugs, we can't factor that in. And so there needs to be a little bit of exploration built in the way that we administer these things. And so let me start with this diagram here. So obviously this would require some preliminary work involving collaborations with stakeholders, data source selection, and collection and design of studies. And then this could begin to feed into this cycle where with the data, we have continuous time individual data collected from sensors and wearables. We use existing databases, electronic medical records, population level, and then that data feeds into the next step where we do management and cleaning in real time, policy learning and evaluation exploration. We do the AI to get the rules and incorporate exploration to that. And then we do model diagnostics and validations, and then we get something that we think can really feed into decision support, and that goes into real-time recommendations, and then it goes into making decision, which may require domain knowledge, and then actions are taken to treat those communities or those individuals, and we learn from that experience and continue to update this. And one of the tools that's very promising is the idea of Thompson sampling, which is an old idea, but has become potentially promising. And that is the idea where you can actually combine exploration a little bit. So you have safe exploration where you're not giving any treatments that are known to be not good for a patient, but you're also close to the optimal and you're moving closer to it, or you stay at a close to it and track it. And this can be allowed to actually adjust if the dynamics of the patients change, the dynamics of the system, of the AI system can change. And so there's a lot of work is still needed for this, but the idea would be to have a healthy blend of appropriate exploration and also discovery of treatment algorithms that's optimizing. So it's sort of greedy and exploration together that leads to some ongoing optimal healthcare that is able to adapt. So that's kind of a big idea. It's very difficult to get there. We need to train a lot of people to help us figure out how to do those things. And so I just want to mention a few ideas. It's very important to do good AI and ML science. Statistical foundation is essential. The concepts of reproducibility, generalizability, study design, and inference are really important. Computing foundation is essential. Domain expertise is essential. And actually, it's clear that there needs to be people that are actually experts at being between these disciplines, and rigorous team science needs to be strengthened. Ethics is an incredibly important part of this. It's highly non-trivial. You need to preserve privacy. You need to break barriers to data use as well. And those are conflicting but important priorities. We need to also study unintended consequences of what we develop and monitor that. And we also need to develop strategies to anticipate and reduce threats from bad actors. Training the next generation with increased democratization, we need to teach the world about fundamental statistical concepts. That's being done by some people, or attempted to be, but it's really, really important that we have the right type of training of people, not just those who are going to become statisticians or data scientists, but all people need to have some level of knowledge of this, literacy in this area. And team science training is very important. Communication is extremely important. The data science and AI experts need a specialized communication training. Also, everyone needs training in data science communication, generally speaking, but we also probably need a new communication subdiscipline that helps in this process, that incorporates AI and data science and helps us be able to track the communication that's really important, because the role of public opinion is really crucial. And we've learned from what I mentioned about the Facebook earlier, that what we do has consequences, and it's very, in society that may not be obvious, it's very important that we work with communication to do this so that we can incorporate that into this process so that it can be integrated into society in a healthy way. Some concluding thoughts. There are many useful new methods in AI and machine learning and biostatistics for precision health discovery. We need to move away from predictions towards decision support. I think in some sense that needs to be a higher priority and recognized as a distinct task that's very crucial. It's difficult, but it's really what is needed. Statistical inference principles are key to all of this. And we need to embrace transdisciplinarity at a higher degree than we are right now. A lot of work remains. Something I heard someone say that I think I like is we have not come this far just to have come this far. So there's lots more to do. I want to extend thanks to my lab. This is the Kosorok Precision Health and Artificial Intelligence Research Laboratory. That name was actually selected about a while ago by the lab itself, voted on by the students and selected by them and other participants. Here's some pictures. This is not the whole lab, but these are the ones that were there when I took this picture just a few days ago, literally. I have a bunch of PhD students, some postdocs. I have some faculty at assistant professor level who are case scholars who are involved in data science and are embedded in our lab. And we have a number of other individuals that participate. One of the faculty is an economist, the other one's a internal medicine physician. So I want to thank them. And there's some references I want to draw your attention to. The review paper Eric Laber and I did in 2019, I think is very helpful to be familiarized with these areas. It's changing, so it's out of date already. And many of the people in this department are contributing to that, advancing. The V-learning work is the JASA paper I mentioned. The composite outcome paper I mentioned is in revision right now. And if you're interested in knowing more, you can go to my website. And I taught a new class this past fall, Biostatistics 740. And all of the syllabus and all of the lectures are downloadable, and the homework assignments are even available. If you want to see some wider array of references and get to know a little bit more about some of the subject matter. And we, in that class covered deep learning as well as precision medicine and the integration of the two. So thank you. That's all I have for now.
Thank you. So we will, we were planning to have a discussion that we posted as 4:35. We're done a little bit early. Maybe we'll invite people to take a minute and like stretch their legs, get some water, take a quick break, and then we'll reconvene in, let's say, 5 or 7 minutes here and do questions and a discussion. Does that sound good?
Yeah. Do you want me to answer some of the questions in the chat?
Yeah, let's go ahead and do some of the chat questions, and then we can take our leg stretching break. That's a good idea.
Okay. Well, the first question here is near to my heart. Rod says, Mozart, on the other hand, was very quick and deep. Yes, there is debate about who the greatest composers are. And it actually depends on whether you're a composer or a performer, what you look at. I will say that Mozart is indeed fantastic. However, I think composers would unanimously say that Beethoven was actually by far deeper, and Bach was even deeper than that. So there is an ordering among composers that's largely agreed upon, and among some music critics. However, there are things that Mozart could do very, very well. In this debate, one of the things that I would say in my friends that are musicians, one of the things that we kind of start to think about is that probably with Mozart, we have less variation. So there's higher number of very good compositions, and maybe less of the ones that might not be so good. But with Beethoven, you have higher variance, but there are many more in the high tail in Beethoven towards actually path-breaking compositions. And we could debate about opera and other things. Mozart was obviously the opera star, but Beethoven was the star in symphonies by far. And that was considered sort of among composers, that's the more intellectual. That's like the novel of music. But nevertheless, operas are important too. Beethoven did do one, and he did a good one, but it wasn't his thing, and so he went on to other things. But that's a debate for other things. However, I will say that for my reading, that's the sense among composition people. But performers will say that Mozart is the top, and opera singers will put Mozart above everybody in the history of the world, including Bach. But anyway, yeah, depends on the angle that you look at. But Mozart is also deep, and he has done great music that's been very influential too. Okay, but that's my opinion. The next question. Why is ST+1 pointing to UT? Great question. This is because the utility is actually a summary of the state. And there could be different reasons. When you get this ST+1, that's the utility you want to measure as a consequence of what happened to your action at time AT. You want to look at how patients have changed. And so you want to look at that. Maybe what was the percent of time they stayed within the safe range? And so you want to factor that in, but you may want to factor in the previous state because you may want to look at changes in state. Or you also may want to factor in the action because you may want to look at the cost of the different treatments you have in your utility. So utility can be a function of the state it's usually considered a function of ST, AT, and ST+1. I don't know if that answers the question. I don't know if Rod wants to get in a fight about Mozart versus Beethoven. I'd love to have that conversation sometime. But let me know if you have any follow-up questions. We can do that also later. Rod also came up with another excellent question. How are limitations that arise from much greater sample size needed to detect interactions rather than main effects? The one thing I will say is a lot of decision support that we're looking at is more focusing on discovery of these rules. And so what we look at is not the underlying parameters. We look more at the value function. And in that sense, it's a little bit like when you're trying to optimize, if you have a quadratic equation, you want to find the maximum, you only need a few points to fit that, and you can kind of interpolate and figure out what the maximum is pretty accurately. There's some interpolation going, but there's other things that are happening here. It's similar to with machine learning classification, where you really want to look at what the final outcome is. You're not so concerned about the etiology of the model you develop. And this can still lead to reproducibility and precision of that value function. So the idea is, if this treatment rule were applied in this population, if I were looking at sample size and power, what would it take? What sample size would I need so that with 90% probability, I can get within 95% of the true optimal achievable value function of any optimal treatment? And that's how we actually often sample power these things, but it's a discovery. You're not trying to do hypothesis testing or even estimate the beta parameters and other things. You're trying to get this thing to work as a decision tool, and you measure the outcome, the actual performance on average. Usually use cross-validation to get that measure of some kind, and sometimes you test it in another population. But you can actually work out the probability of reproducibility. So it is a slightly different paradigm than the traditional etiologically based regression modeling and hypothesis testing, which is also a very important paradigm. But that's part of the reason that we can do this. You look at sample sizes that are likely to get usefully reproducible rules that will benefit. And then we often work to also come up with interpretable ones based on that first black box that also are close to being as optimal, so at least we can have an understanding of what's going on. But there's a big discussion about black boxes versus, that wasn't what you asked, but that's kind of related to this. Okay, that's one answer. And then another question that was asked is, in the diagram, perhaps also an arrow from domain knowledge to preliminary, which involves design of studies. Yeah, that's a great idea. And I think that when we put stakeholders, we included domain knowledge, but it'd be good to make that explicit. That's a very good point. Those are all the questions that were in the chat.
Great. Okay, so maybe we'll take a 5-minute break just to let people get up and stretch, and then we'll reconvene here at 4:35 for a discussion.
Michael, are you there?
Rod, we're just taking a break for 5 minutes and
Yeah, no, I was just going to say hi if he was around.
I think
Since
he went to get.
I didn't meet with him, so of course I
What
could
are you
complain.
a Mozart debate? Did you? Was that the goal?
I think Beethoven was more path-breaking than Mozart.
I think Mozart's music is nicer, personally.
I think so too.
So
in this
Beethoven wrote some incredible stuff. So. But the way he wrote things out was more a feature of his personality, I think, than whether I wouldn't necessarily rate composers on greatness based on how messy their manuscripts were. But Bach, of course, who was probably the greatest of them all, had pretty good handwriting, I think. So he wrote pretty well. Although he had people to transcribe a lot of his music, so he always used to complain. So Bach would always complain that people would get it wrong when they copied things, because he had very little time actually between writing stuff and performing. So eventually he couldn't write it all down himself. So particularly since they had to write out all the individual copies for the everybody in the orchestra. So. I think Michael's right that I don't think machine learners can quite emulate the great composers. I thought it was interesting what he was saying. Brahma, since you were in Michigan Society of Fellows, I think I was intrigued by what he was saying about the differences between the artists versus the scientists. So.
Yeah.
The artists are just totally after things that are novel. So.
This is true. But in some sense, I think if you think about the most abstract form of science, people are also pursuing that in some sense.
Yeah. Right. Otherwise.
I was telling Jim Cogswell that I never, before the pandemic, when I bought his paintings, I never thought that I'd spend so much time looking at them.
How is Jim?
He's doing well, yeah. I was looking forward to the celebration of the Michigan Society of Fellows, which did not happen, right? So.
All right. I think I couldn't go, actually. I had a conflict. So maybe they'll do it some other time.
Then you can go.
Mm-hmm.
So. Did you watch the debate?
No, I was actually, since Michael's back, instead of watching the debate, I was actually listening to Bach, so, which was a much better idea.
Actually, that sounds like the way better choice. I made the misfortune of listening to part of the debate, and I had to recover for a while afterwards.
Well, we reckoned that if we actually listened to the debate, we wouldn't be able to get to sleep. So, for that reason, we didn't watch it. So.
Yeah, we watched it for like 5 minutes and then turned it off. So you are wiser than us.
Yeah, my wife said that was a good decision. So, having seen what happened.
Yes.
Anyway, it's good to see you, Michael. I like your talk a lot, so it's fun.
Thank you.
I was saying, I think Beethoven was probably more innovative than Mozart, right? He sort of went off, particularly when he became deaf. He did this stuff that was totally incredible.
Yeah, yeah.
And totally outlying, but it's amazing to me. I don't. Mozart's not probably on the top of my composers, but he is deep though, I think.
Yeah, I mean, I would say his operas are probably his deepest things. His Don Giovanni.
Yeah, I'm not so keen on his symphonies. I agree with you on that.
Yeah, I mean, I would say
I like his
40th
piano
Symphony.
concertos.
40th Symphony is, I would still put in the top list of symphonies. 40th Symphony probably makes it to my top 5 list of symphonies, but Beethoven has two or so symphonies on that. But his operas, I mean, still, and some of his comedies. What is it? Marriage of Figaro. Some of the extended counterpoint comedy scenes where all this stuff is going on and craziness. It's just pure genius. It's amazing. Yeah.
He had Ponti to help him, so it was obviously very talented.
Yeah, it's good to have a good librettist when you're writing an opera. Makes a big difference.
Magic Flute is my favorite.
Yeah, I think many people list that as a top. I like it a lot of his operas. I think that because it's been kind of overplayed, I kind of like Don Giovanni a little bit more right this moment.
Oh yeah, well, Don Giovanni's fantastic.
Yeah, but I also like a lot of his other operas too.
Well, first act of Così fan tutti is incredible.
Oh yeah, and other parts of that too. Yeah, he has about 4 or 5 operas I would say are top operas of history of opera. Yeah.
So are you composing then with your?
I am actively composing. I've been doing it. I returned to doing it actively about a year and a half ago. I try to put in 10 hours a week if I can. It's very hard to do that sometimes, but I just feel the need to do it. So I've been doing it.
What sort of things do you compose?
Well, the first thing I did when I got back was a choral work for an Advent sort of thing. About 11 minutes. I kind of brought in some Renaissance style music into modern classical. And I'm working on actually a symphony right now.
Oh, nice.
I'm into the 4th movement, a 37-minute piece. It's a horrendous amount of work and I'm finding myself frustrated 2 out of every 3 days. But it's moving forward and it's producing sounds that I like. So that's kind of my bar, and my family members like it as well. So that's my other important critic. My wife being the most important of all the critics. She's got very good taste, and she's willing to laugh at me if something sounds dumb. She's not worried about hurting my feelings, and that's actually pretty useful. Anyway, but
I sang in this virtual choir, this Sing Gently.
How's that work on a virtual choir?
It's everybody sends in their own recording and it's all synchronized on a clap, so everybody follows. You have to follow the conductor very closely.
Oh, okay. So you synchronize with the conductor and you listen to it, but it's not you.
You're listening to it with an earpiece, basically, but you're recording to another device. But that Sing Gently was amazing because they had 15,500 singers from 128 countries.
Wow. So what did you guys sing?
This was a piece by, I'm having a senior moment. I'll tell you in a second. We probably shouldn't talk about music all the time.
Michael, there are a couple of questions which are related to petition. Yeah. So maybe Veera, you want to unmute yourself and ask your question?
Yeah. So back to mundane stuff, I guess. No. So Mike, that was a great, I think that was the way you laid out the framework and different usages and utility of it. That was quite informative. So I always had this, when I give my talks, like I come from a systems perspective, that when I talk to clinicians, there's always this need of, at least in cancer, of knowing the mechanism. How do you precisely know the mechanism of either a disease outcome or a treatment outcome, and how do we get that? And then, when we do black box type models, the focus is more on prediction. So I guess I just wanted to hear your thoughts now. How does one reconcile the two when one wants to go when you have models, systems-based model where the parameters can be, exactly linked to, disease mechanisms versus, purely black box models. So that was sort of a high-level question.
Yeah, I think that's a really important question because we have, both of them are useful parts of our research process. Black boxes can be used to kind of get an initial idea of what you need to fulfill a task. But you often want to get the etiological understanding of what's going on. And sometimes these are kind of incompatible with each other. Sometimes you can't really get a good decision rule with any existing modeling approaches based on what's known about the mechanisms. You just have to kind of say, okay, I have no idea. One of the interesting things that you can show that's sort of related to this with reinforcement learning is if you are trying to look at the sequence of actions, there does exist a dynamic model underneath it involving, some sort of mechanistic structure like differential equation of some kind. And what's interesting is that you can show that reinforcement learning actually solves approximately these differential equations to get these actions in some cases. And that I think is kind of interesting. It's sort of, you think of it as an approximation to working around the mechanism, but actually incorporating it, blindly through these black boxes, but it's incorporated into it so that it actually makes the right decisions, but it doesn't give you the ability to get at the underlying mechanism. But sometimes there's so little known about the mechanism. And sometimes you can use these things to learn about the mechanism, to go and then interrogate the black box to see if there are things you can find out about it. And there's sort of simple ways to do this, such as just seeing if you can replace a black box with a decision tree or a list decision list or a linear model or something that's more interpretable. But there are other things that are maybe more challenging where you may want to try to extract some sort of differential equation from it. I haven't worked in that latter area very much, but I do know some people who are interested in this. There's a very interesting work being done that's in the works by a person named Andrew Wilson at New York University. He's a Cambridge-trained AI specialist, but his background is he brings a lot of statistics into it. He uses a lot of Bayesian methods and a lot of statistical ideas. And he's been working on bridging these black box deep learning tools with estimation of mechanistic models. So you can get not just regression coefficients, but dynamic systems estimated. And he's made some progress in some ways. I think there's a lot of interesting work, and this is a hard question. However, I think there will always be the case that we may want to move ahead in terms of treating patients beyond what we understand biologically. And that's really what the value of a black box can be. But one needs to interrogate these things and check them. You can't just hope for the best. I think one of the things we've discovered in some of our work when we're looking at building these regimes, there are ways to directly estimate a tree that optimizes the outcome. It turns out that for whatever reason, that's a very nonlinear, very difficult problem to solve. And we found that sometimes easier if you start with a random forest that approximates things and then break off pieces of the random forest and get in different careful approaches, break off little pieces of the tree from that random forest and carefully step through using the random forest to generate your tree. You can do that in a way that you can get really, really powerfully better trees that really give you good treatment regimes than either the random forest or the original effort of getting the tree. It improves on the random forest by quite a bit, but the random forest is very useful at bringing along with it these interesting interactions that are harder to keep track of. We don't know all the reasons that it works, but it seems to be verifiably something that's really happening. So I think that there's work on this, and I think it's an interesting question, but I feel that the utility of black boxes will always be there, and the importance of etiologic models will always be there. We'll have a little bit of tension between these two, but I think they're both useful tools in our quest for precision health.
Yeah. Thanks, Mike. I think that's a good point you make, like going from machine learning and refining it to make it more, more amenable models in some sense. I usually think the opposite way, that start with a simpler model and complexify until you get the right sort of optimal optimal rule or optimal behavior that would make the data generating system.
Yeah, one of the interesting examples I like to use to sort of show it's not always going to work is because there may be structure that your simple models just can't ever find if you start from there. An example that I like to throw out is trying to train a automated pilot to fly a helicopter upside down. That's a really, really difficult task. And it isn't clear how to do that directly from modeling, but you can actually use simulations and reinforcement learning and effectively figure out the things you need to do to work on that very unstable setting. And there's a guy, Andrew Ng at Stanford, who's done this work. You can find a photograph of this autonomous upside down helicopter that he's trained to hover nicely upside down. It's very impressive, considering how aeronautically unstable it is. It's very impressive, I think. So my point is that that's not directly related to this, but I think it is in the sense that I think that there's some structure that's relatively additive and linear, but there's a lot of other structure in medicine that we don't fully understand yet that I think has to be interrogated by black boxes first before we really will understand. Others will benefit from interrogating through more traditional linear models and other kinds of models that are less black box.
Thanks.
So I have some questions from the chat. Should I respond to some new ones, I think?
I mean, Jonka, you asked one before me. I didn't want to cut you off before you.
Go ahead, Walter, you asked first.
Hi,
Go
Michael. My name's Walter.
Yeah,
nice to meet
I
you.
saw it. Is your question. I'm just pulling it up.
Okay, great. Yeah, I was gonna say I can say it out loud. So my question just comes from a lot of interactions with clinicians, and I really liked your talk because one of the struggles I've had. You mentioned Thompson sampling, and I think just using that as an example of this issue where, if I tell someone that I'm going to continuously learn on someone, but never really necessarily end up at a deterministic policy, but sort of always have randomization in the background, I think I've had a hard time convincing people in other areas to let that be the case. So I was just curious about your how you handle that kind of conversation with clinicians. And going to Vera's point about interpretability, one of the ways I've thought about it, and I was curious your thoughts, is potentially the policy that you're going to implement might be parameterized in a way where some of the states are interpretable. So we've had some settings where stress was used in the policy and things like that. So the clinician can see that stress impacts the policy in these ways, but that not the dynamics weren't built in there. So I was just curious about those two different aspects of things and your thoughts.
No, that's a really good question. I mean, I think that there's still work to go to define what it means to do safe exploration. And I think that we have to kind of learn to think culturally differently. I've been working on, I talked to some people earlier. I feel the challenge of doing something at this level of difficulty and complexity, the idea of Thompson sampling, the concept of a continually random search, in a way, this happens in nature because there's error in the things we try to do. Fortunately, our own brain AI does not ossify too quickly in our lives, or we'd be in real big trouble. I guess it happens for some people, but anyway, I hope but it's not a good thing usually. It's not one of those things. We want to have that little bit of exploration continue into our lives, and nature kind of gives us the opportunity somehow. So what are safe ways that exploration can be done in this context? One certainly would stay away from treatments that are known to be bad or known to be extremes, but in some cases, tweaking the dose up a little bit or down a little bit within a safe range may not be, we don't have to do really wide explorations here. And so, but this is the point I was trying to get to, is in general, a question in data science is how do you implement new developments in data science and get people to adopt them? If you go to many, many disciplines, they have this solidified approach to research in some cases. How do you get them to consider to use something besides a generalized linear model for their particular thing? Or how do you get them to think beyond other kinds of models that are being used and that are sort of widely used in those areas? And how do you do that? And it's an open question. And so I actually think that there is room for research in how to, in science as a whole and scholarship as a whole, how do you get people to being able to continually progress? You don't want to make rapid changes all the time. That's not really what we're talking about. But how do you get people to be open to progress? Because everybody's close to it. It's not just, and actually we statisticians can get in this situation where we have a particular type of method that we say is tried and true, and we just like to use it. And everything suddenly, it took a while for people to adopt the Cox model, right? And now it's taking a while for people to adopt other models like accelerated failure time. There are settings where that's really, really useful, and other kinds of models. And that's I just don't know. I think that's a culture of science, anthropology of science question, but I do feel it's an important one. And I actually am working with somebody at UNC who is looking at creating a program that looks at, that wants to do this person literally wants to study this for a couple of years. How do you bring system science into the tools of system science, into the process of helping clinicians adopt new technologies, particularly precision medicine or other technologies? How do you look at the culture here and what has to happen? Because I will say that there are clinicians I work with that are completely on board. They love this stuff and they get frustrated that it appears they don't understand it. And they're not statistically, they don't know as much as a statistician does, but they get enough that they can see the big picture and they can kind of understand the underlying philosophy, and it coincides. They figured out how to make it work for them, but they're not the rule, right? They're just a small number of these. And I'm not saying that we should just adopt every old thing. There has to be some sort of evaluation combined with introducing, combined with education, and then gradual adaptation that doesn't take forever to accomplish. And we have to be able to become healthily facile in this process. And I don't know what the magic ingredient is that. I don't think it's just we have to learn to communicate better. I've learned that it's more than that. It requires people that are in cross-disciplinary fields who know a little bit of both that can bridge these gaps. There needs to be specialists in some cases to make these connections. And we can't just blame the communications problem. No, we like to think that we all have trouble communicating, but actually statisticians are pretty good. We just have our own culture, and that's part of the challenge we have with communicating. But even there, some people that are in the clinical world and in the statistical world can bridge gaps that we just can't bridge, even if we have a master's in linguistics or in English or something that gives us great communication skills. There's more to it than that. Anyway, I feel it's an important issue. I don't have a real good answer, but I feel it's worth working on.
Thanks.
I think Jenka's question was left out, so Jenka should have the chance to ask.
Oh, I'm sorry. I didn't.
That's fine. I have been thinking about what you said, which is totally deep. Yeah, so my question was more technical, I think. Tailoring variables, I think this is central to the ability of adapting treatment actions. So what if the tailoring variables are missing or partially missing? So this happens a lot in the studies I've encountered. For example, if we're going to send a message on app, but what level of message, like more stern worded, more gently worded message, needs to depend on, say, how many steps you walk in the past day. But what if I did not wear my Fitbit, just by accident or for some other reasons? So that information is not available. So currently, the practice is to default to a certain level of just medium level worded message. So it does not sound too stern, does not sound too gentle, just medium level. So I wonder, more broadly in methodological context, this must be a real issue. I don't know whether you have encountered them or not, and if so, what is the
Yes.
approach to address them?
I have you know, I used to try almost all my power to ignore missing data as an issue. I really tried, but it's not possible, especially with these kinds of projects involving this rich kind of data. They're ubiquitous. Missingness is ubiquitous. Imputation is really, really important. I will say that there's been a lot of great developments in this area. And I'm looking right at, you guys have some of the world's experts in this question, and there's continued to be some interesting developments. I'm very excited about some of the recent works combining random forests with mice, multiple chain equations, and there's other approaches that you can do, but I think one needs to think about what to use in a given situation. Multiple imputation seems to be usually very important because there's dependencies across these variables. And I just don't think single imputation works super well in these cases, but that's just my opinion. But there's a few gaps in some of the existing software for missing data that I think that if a handful of experts were to really work, we could fill out that software. But missingness in machine learning is kind of a unique challenge. And it turns out that one can consider the machine learning specific goals and sometimes get improvements in imputation. So I think this is an important issue. I'm trying to think of a good, so what we've been doing is we've been basically doing a combination of random forests with mice in our work. And basically we sometimes have to, there's something called misforest, but the software is kind of hardwired for a single imputation, but the concept can be extended to multiple imputation. So what we've been doing is we've simply been developing our own software to be able to do this. But I wouldn't necessarily trust it enough to share with everybody. We do multiple copies and we check it carefully. We even examine the joint distributions of the missing data compared to the non-missing part to see that they're roughly matching, you know, using various things like crude levels could be mean, but you can look at covariances too. And I think Rod probably has some better ideas about this than I do, but I think this is really, really important. And I feel that I've been impressed with what random forests can do, because when you do a random forest, you can simulate. Random forests are not for predicting means. You can actually generate conditional distributions with random forests. And this is where this can be really, really useful for kind of a generalized implementation of mice, which I think is a very beautiful approach to imputation. Now the question is, what I would say at a higher level, I think that if you look at our x, a, and y variables, I think you want to do imputation at x alone and not bring a and y in, since you're going to be using them to sort of predict those things. I think that kind of does some stuff statistically I'm nervous about. And then I think it's maybe okay once you do that to maybe use x and a to impute a, and then y. You know, one has to think about these things. I actually would probably not impute either the treatment or because of the crucial role they play here, but there might be settings where you might be able to believe. For example, if you really have a propensity score that's good, where you could impute the A's once you've imputed all the X's. And then I think imputing Y, since that's your thing you're really target, that makes me even more nervous. But there's sort of a staging going on and what you need to impute and what's important as you go along. And that's at a high crude level. I'd be interested to know what Rod thinks about that. But I think it's really important, and that's the sort of approach we've been doing.
Well, if I could respond, so the idea of doing chained equations with something like random forests, I think is fine, and I would personally like. I kind of like BART. I think BART because it's sort of within
a random forest for the
because it's kind of within the paradigm of chained equations. So I don't know if Raghu, who has a software program, is working on that. I know that there are people at ISR who are working on these kinds of things.
I think that would be a very, very valuable tool to have it. Right now, there isn't a fast tool, and we're dealing with tens of thousands of observations. You bring down, even cloud computing starts getting broken at that level.
But I just want to disagree with what you said at the end, if you're imputing draws in a chain equation thing, you need to condition on everything. So you should not omit the outcome when you're multiply imputing X. That's a mistake. And if you want to see why in a very simple setting, I have this review paper on regression that I wrote back in '93 that I think.
Well, I'd be interested to see that paper.
It's a question of whether you're imputing a best prediction versus imputing a draw. If you're imputing a best prediction of X, then you don't want to include Y. But if you're including a draw, you have to include Y. In fact, otherwise you're biased. So the principle of conditioning on everything is important. And if you're doing something like precision medicine type settings, and you have to be careful to include interactions there, because you don't want to miss the interactions that you're after when you're doing the imputation.
Yeah, and so that's where
which might be why something like regression tree type stuff might be good.
What'd you say? What was it?
Well, it might be that since the focus is on interactions, you want to at least make sure you have interactions in the model. And and tree type models tend to have more of a focus on interactions. So so there might be some advantage there. So.
Yeah. So we do agree on the random forest being a useful idea, and I appreciate your insight too on the dependencies among the other variables too. That's a really good point. But I do feel that software that's usable for this situation, that's fast. I think something like you described, implementing BART, would be really, really powerful, and certainly we would sign up for it, I'm sure.
Well, I'll tell Raghu he has to get onto it immediately.
Yeah, we're done in a hurry. We need
Otherwise,
it yesterday.
his chair will get onto him.
We need it yesterday. See, there's another one.
Hui has a question.
Oh yeah, how to effectively train biostat students on ML optimization computing, given that they already have a heavy load of biostat curriculum? Yes, this is the question. So recently we changed our data science curriculum for our PhD students, and we actually we combined some courses and shrunk our material for them, and we removed a few other courses. So one of the things we did is we used to have SAS be the first semester if students didn't have it. Now we just expect them to have SAS. They need to do it the summer before they come in, because it is expected that they'll know it. But we have a little boot camp to teach SAS. And actually SAS has some material to help this happen. And now we have them take a data science course their first semester instead that teaches them Jupyter Notebook, Python, tricks with R, reproducible research, visualization of data, and many other data, GitHub, and all of these sorts of tools, and has them become quite familiar with them. And students think it's a pretty hard class, but it's really rewarding, because then one of our new classes we have is we revamped an old computing class, and we now make it required. And we got rid of one of our electives, so students now only have 3 instead of 4 electives required to fill this in. So we didn't have to have a net increase in courses. But anyway, and with that class includes optimization, Bootstrap, machine learning, and other things, sort of with the assumption they've already taken the data science course. So they're sort of doing, most of our students are doing very cutting edge data science and machine learning by the time they finish their course sequence. One of the things we ended up giving up was we combined linear models and generalized linear models into one class, and cut some of their curriculum down. So we only have one PhD course in linear and generalized linear models instead of 2 for both of them. And it's still a large and big course, to be honest. It's still our toughest course, but it's reasonable. So that's some of the things. We did not decrease our theory per se. We did not cut back on that. But the computing class is hands-on, and we're also going to be the plan is to have the computing material be included in the qualifying exam, so that their students are very motivated to get this stuff down. So those are some of the strategies that we're working on at our place. But I will say that that gets you to a certain point of literacy. I will say that I think for some of the material here, it takes a lot longer to learn the material. If you want to have deep learning, for example, if you really want to get good at it, it's similar to learning empirical processes. It takes a lot of time and practice. There's a lot of tricks to learn, a lot of familiarity with many tools. I usually like, compared to other things, I usually think it takes a student a good 6 months if they're working almost full time on it. It's not a one class thing, although I think it's good to introduce it in a class. But that's something that we don't require all our students to know that, but in my lab, I have a bunch of students who specialize in that area, and it takes a long time to train them. So some things are not going to be fast. But I do think it's really important to shift this because biostatistics, I think, as a discipline is shifting some.
Thank you, Michael. That's very, very informative to know your curriculum change.
Okay, well, if that is the end of the discussion and we're right at about time, so that might be a reasonable place to wrap it up. Just thank our speaker and thank you for taking the time to talk with us, and thank you everybody for coming, and we will see you again next week.
Thank you so much, Michael.
It was great talking to you. I wish you all well.
Thank you.
Thank you, Michael.
Bye. Bye-bye.